Hello, everyone. Greetings from Seattle. I am sorry that I can't be with you in Leuven today, but I'm happy that at least I get to give this recorded talk. Today, I will talk a little bit about multi-level, multiple imputation in EMA research, why you should care about it, and how to do it, sort of a gentle first introduction. Um, Quick disclaimer, I'm not a statistician. I'm an applied researcher like most of you, and that means that you should take everything I say with a grain of salt. These slides, the code underlying these slides, and this recording can all be found on the OSF via this link down here. As most of you know, EMA research is synonymous with missing data. We always have missing data in these studies. And statisticians will tell you that there are three sources of missingness. Data can be missing completely at random, and not at random, which is very confusing terminology. But really, as an applied EMA researcher, I think there are two sources of missingness. Either you know why your data are missing, and then they are typically missing completely at random, and of course that missingness can be safely ignored, or you don't know why the data are missing, and then we should assume that the data are missing not at random, because that's plausible and most conservative. And of course, we always have missing data in our study where we don't know why the data are missing. The problem is that when data are missing not at random, this can lead to biased estimates, even when using full information maximum likelihood, which is the default setting in most mixed effects modeling softwares. For example, let's say we do an EMA study to understand the daily within-person association between mood and drinking. That's, of course, something that I study a lot. Let's say participants respond to 5 surveys a day. At each survey, they are telling us how they are feeling right now. And then also every morning, a person is telling us whether they had any alcohol the night before. Let's just accept that that is the design. The problem here is that it's very intuitive that a person might be less likely to complete a survey in the morning when they got drunk the night before. I think that makes sense for everyone. And maybe it also makes sense to you that participants might be slightly less likely to complete a survey irrelevant of time of day when they are highly distressed right now. Full information maximum likelihood cannot handle this case. We can quickly show this with a simulation. Here I simulated basically the study I just described, and I'm generating 2 datasets. One dataset in which we have no missingness, and one dataset where we have missingness. Of course, no missingness represents an unrealistic scenario where we get every single participant to complete every single EMA survey. And in this simulation, I'm making it true that when a person's mood is worse, they are more likely to drink. But I also, and in the missing dataset, I give every survey a baseline probability to be missing, but then I increase the probability either if it's the morning and the person got drunk the night before, or when their mood is really bad right now. And if we then fit the FIML model to both of these datasets, we can see on the left that in the complete data scenario, we recover the true association that I simulated, an odds ratio of 1.4. So worse mood, higher likelihood to drink. But then when we fit the FIML model to the missing data scenario, we can see that we are really misestimating the odds ratio, the effect size. And the reason this happens is because in my simulation, yes, it is true that lower mood is associated with an increased likelihood to drink, but also it is true that people are more likely to miss the morning survey when they got drunk the night before, and they're more likely to miss a survey when their mood is really bad. In this scenario, FIML will not save you, but multiple imputation has the potential to do so. It will not do so automatically. So I'm going to show you now how to perform a multi-level, multiple imputation with the mice package in R. Here I simulated another data set. It's essentially the same study, but now I added a baseline and a few extra EMA items. And the missingness is a little higher. Now it's 38.7%. And as you can see here, I simulated a very simple example where either a row of data is complete or the baseline is complete, but the participant is missing the entire EMA survey. And this is certainly the most common pattern of missingness in our data. But of course, in real data, you would have additional sources of patterns of missingness, right? Sometimes participants skip a baseline item, they start an EMA survey and don't finish it, and so on. But this doesn't really change anything going forward. It's just good to first visualize what you're up against. And then in mice, when you want to do an imputation, you always need to do 2 things. Sometimes you need to do more, but you always need to do at least 2 things, and that is specify the method and specify the predictor matrix. So here in this code, what I'm first doing is I'm initializing an empty mice object. By setting the iterations to 0, I'm telling mice basically get ready, but don't run it yet. Because that allows me to then conveniently customize the method and predictor matrix to my liking until I'm happy, and then I run the imputation. So here you can see that for each item that has missing data, those are the 5 EMA items, I am specifying which method to use to impute it. And all of them are multi-level because all EMA items are nested in participants, and that needs to be accounted for, just like in our analyses later. So for instance, for mood, I'm using multi-level predictive mean matching. In my experience, this is an imputation method that works really well for variables that are continuous but have funky distributions, so which are highly skewed, bimodal, that kind of stuff. Of course, if you have a nicely normally distributed variable, then a linear model might work well. And then for alcohol use, this is binary. It's just 1 I drank, 0 I didn't drink. Because it's a binary item, I'm using a multi-level logistic imputation method. So when we print the method, we can see that the method is exactly what we want for the items that have missing data, and it's empty for all other items because those have no missing data and thus do not need to be imputed. You could also change the method of an item with missing data to be empty. That would tell mice not to impute it, even though it has missing data. And of course, if we had missingness in the baseline variables, then we would need to specify a method for those as well, but it wouldn't have to be a multi-level method because those items are not nested in participants. Assuming we are happy with the method, we can move on to the predictor matrix. So here again, because we're only imputing EMA items, we can just generically set the PID column to -2. -2 in mice means this is the variable in which other variables are nested. And again, if we also had baseline items, then we would need to be more nuanced because those items are not nested in participants. And then for each item, and I'm really spelling this out here so that you see what happens, for each item that I want to impute, I need to specify which variables to use and not use when it comes to predicting / imputing the missing item, right? So here, for whatever reason, I'm deciding to use all of the items that I have available, except for the big 4 traits here. I accidentally forgot to simulate neuroticism because I'm not a personality psychologist. Don't spend too much energy right now on trying to understand why I'm doing this. You are the expert in your line of research, so there you will be the one that decides what to use and not to use. I'm using a very similar model for mood, and I'm using a very much simpler model for peer context. So then we can print the predictor matrix for alcohol use. We can see PID is -2. All the items we want to use are 1. All the items we don't want to use are 0. That looks good. The item that always needs to be 0, of course, is alcohol use, because an item cannot be imputed from itself. Assuming we are happy with the method and the predictor matrix for all items, we can then run the imputation. So here I'm generating 20 imputed datasets. Before we can analyze these data, we need to make sure that the model converged and imputed sensible values. So we will look at a few diagnostics. One thing you should look at is the PSRF. That's essentially an R-hat statistic. It's the ratio of within to between imputation variance. And towards the end, it should be stable, close to 1. So here down here, it should be close to 1, and it is for alcohol use, and it is for mood. So this looks good. This is an indicator that the model converged. We should take a look at the trace plots to make sure that the chains have mixed, just like in Bayesian statistics, and this looks good as well. I like to make a plot like this one, where I compare the distribution of the imputed variable in the observed data and in the imputed data. And of course, they should look roughly similar. So here 0 is observed data and 1 through 20 are the imputed data sets. The distribution doesn't need to be exactly the same, but certainly if it's really off, then you know that something went wrong. So for instance, something that happens often in my research is that in the observed data, I have a variable that has really a heavy skew, and then it comes out perfectly normally distributed in all of the imputed data sets, then you know that something went wrong. I also like to grab one of the imputed data sets and plot the imputed against the observed values. Again, these don't need to map onto each other one-to-one, but this can tell you if something went wrong. So for instance, if all the red dots, all the imputed values are in one corner, then you know that something went wrong. So this looks good. Now that we have made sure that the model converged and imputed sensible values, we can compare the results once more. We can see that in the complete data scenario, we are again recovering the true association, this time an odds ratio of 1.42. The FIML model fitted on missing data, again, is quite a bit off. But then if we pool the odds ratio over the multiple imputed data sets, we get very, very close to the truth. Now, the reason why I get this close to the truth here is because I know why the data are missing, so I can make sure that I account for it in the imputation. In the real world, where we don't know why data are missing, this is not necessarily realistic, but it is realistic to reduce the bias, right? So for instance, imagine we would estimate a pooled odds ratio of 1.35. We wouldn't get it exactly right, but we would be closer to the truth than with a FIML model. So how do you pool the information across the imputed data sets? I'm going to show you this quickly. In the frequentist approach, the code looks really easy, right? So all we do here is we fit the model to each of the data sets. So here imp is a list of data sets. We pool and then we get an output like this. Looks very easy. However, conceptually, pooling across imputed data sets is not easy in frequentist statistics, because in frequentist statistics, there is no real solution to incorporating different sources of uncertainty into the model. And that's why we need to make a lot of assumptions and some workarounds that are quite ugly, I think. I'm not going to go into too much detail now, but if you plan to do this, you should read up what you're up against. Rubin's rules is what you need to look for. Things are much easier conceptually in the Bayesian world, and that is because in a Bayesian model, all parameters have probability distributions that automatically bakes every source of uncertainty into the model. And what this means is that we can simply combine the posterior draws from all the models and arrive at one posterior distribution, just like we would if we would fit one model to one data set. Here, by the way, we get the exact same result. So more computationally intensive, but much more straightforward conceptually, requiring fewer assumptions and workarounds. There's also an advanced Bayesian approach in here that I'm not going to cover now. Only in the Bayesian world, you can essentially skip the multiple imputation and impute directly during model fitting. This is advanced. I'm not going to talk about this now, but it's here if you want to take a look. I want to end by mentioning a few things I didn't mention so far. One is that often in our EMA research, we have scales, right? So instead of asking a person one mood item, we might ask them how angry, unhappy, sad, anxious are you right now, and then average those items to get an indicator of negative affect. If we plan to compute this scale after the imputation, we should passively impute this scale during the imputation model. So here's how you do that. You initialize a new variable in the method called mood negative, and you tell mice how to compute it. And then you need to make sure in the predictor matrix that this scale is only predicted by its components and nothing else. And the reason why this is important is twofold. One, it will lead to logical consistency. You will not impute a combination of values that is impossible, and it will maintain the proper relationships between the items in the scale. For a very similar reason, if you plan to test an interaction in your data after imputation, you already need to specify this this interaction in your imputation, right? So here in the method, again, I'm initializing a variable. I'm telling mice how to compute it. And then in the predictor matrix, I need to make sure that this interaction is only predicted by its components and nothing else. One more thing I want to mention is that so far I'm making this sound relatively simple, and it really isn't. You are going to run into a lot of issues. At times you will have no idea what's going on. You will have to consider different imputation methods. You're going to fail a bunch. This is going to slow you down. And at the end of the day, it's going to be just a little bit of trial and error to get it to work. Every new data set is going to be a new challenge. I hope that I've convinced you today that it is worth investing this time to learn how to do this and slow down your research. The last thing I want to say is that when you plan an EMA study, you know that you're going to have missing data, and now you also know that FIML is most likely not going to cut it. What this means is that it makes sense to already plan for the multiple imputation at study conception. One thing you can do is you can collect auxiliary variables, both at baseline and during the EMA, that are likely to predict both the fact that a value is missing and the value that you need to impute. And that will certainly help improve your imputation and reduce the bias. You can consider planned missingness designs, because then you know why some of the data are missing. They're missing completely at random. Though in my experience, there's also too much of a good thing, and then you run into issues as well. Lastly, you can add items to your EMA battery that directly contain information about the missingness. For instance, if the participant misses the first survey of the day, you can ask them at the second survey of the day, why did you miss the last one, with a checklist, and then you can use that as an auxiliary variable in your imputation model. I'm running out of time, so I'm going to shut up here. I hope this was useful and interesting. Take another look at the slides, take another look at the code, And if you have any questions, don't hesitate to reach out to me via email. I'd really be super happy to help anyone with their first imputation. Bye.